Right. Okay, good. Okay, so today's topic, we are starting on oscillators, and on here now. I don't particularly like the definition, but it was one that was taken from a textbook that we use. I may have to change this. That oscillators deliver a sinusoidal output waveform without input excitation. Essentially, oscillators deliver a periodic waveform without excitation. This bit here, without the input excitation, is the key, the crux of the matter. It can deliver all sorts of shapes. It doesn't necessarily have to be sinusoidal, but the type of the circuits that we're considering right now are those that happen to deliver sine waves and cosines without this input excitation. It is an interesting thing, right? And of course, we use oscillators around the place. A big chunk of the application of oscillators are in communication systems. Computer systems use them to generate clock signals and so on as well. And then they range from a variety of frequencies, from extremely low, so they're sort of below the fractional hertz signals, all the way up to tens of gigahertz at this point in time. And in many cases, low distortion is required. What that means is that the sine wave itself, you have done Fourier series as well, and you know that signals, depending on what this signal looks like, the signal itself has harmonics, which are not only a fundamental frequency, the main frequency, but there are multiples of that exist, and we'll talk about that. But every time you have a signal and you have harmonics or extra signals around there, then the signal is experiencing distortion. And what you want in oscillators is to generate a signal that is as clean as possible with very few harmonics around. That's what they're talking about here. And there are two main classes of oscillators. There are those that use resistors and capacitors to generate the oscillator output. And those are useful from fairly low frequencies up to about 10 megahertz. So they're generally used in audio applications or in low frequency radio applications as well, but mostly in the audio to slightly above range. And then the oscillators that use capacitors and inductors are the ones that you tend to use now up into the high megahertz range. Those are the ones that you use to generate the sort of carrier signals that we use for the cell phone networks and for RF radio frequency communications and satellite communications and the like. All right. Our particular concern at this point in time will be looking at the RC oscillator. Now, there are certain conditions for oscillation to occur, and we got a taste of that. Those of you who did who were doing signals and systems were in class this morning. We were talking a little bit about some system responses, and under certain conditions, the system can oscillate. And we said for certain applications that wasn't needed, but there are other applications where you may want it intentionally to oscillate. So let's look at what these conditions are. And to do that, we're going to have a little introduction to something called block diagram representation, and a second look at something that we've met before, which is something called feedback. Okay, so look at this as a soft introduction to something that we're coming to in signals, but it's very straightforward, and it's something you need to know, whether it's electronic signals, communications, or whatever. Okay, so here's something called a block diagram representation. What we have is a system. The system has already been represented by its Laplace transform parts. So this is a Laplace transform of the input, the output, and these are some blocks in the system, or components in the system, if you like. This particular one has a transfer function GS, and this particular part has a transfer function of HS. And we use this sort of this is the simplest model of a block diagram, and it's a particular type of model called a feedback system. Okay, so let's see how this works. This particular example has negative feedback because, as you see, part of the output is going through something here, and then when it's coming back in now, it is being subtracted from the input. So the input minus some part of the output, right? Ys is equal to or less than y1s is equal to or less than ys. So there's a part of the output coming back here that is being subtracted. We call this negative feedback. And this whole thing is what you call a closed loop feedback system. All right. So it's fairly easy to show, and we will do it formally in the other class, but it's fairly easy to show that the relationship between y and x is that y is gs over 1 plus gshs, or sometimes we simply shorten it, since we know that everything else is in the Laplace domain, that y is equal to g over 1 plus gh, right, times x, where we understand that this means x, that in the Laplace domain, x of s, g of s, h of s, and so on. How you would show that, of course, is that you get, you say, for instance, that gs here, or ys, which is the output here, is x1 by g, okay? y1 is y by h, and then x is x minus y1. And if you eliminate y1 and x1, you will end up with this transfer function. And we'll do that formally, okay? We'll do that in the other class formally tomorrow. But to remember this, and by the time you finish this class and the next class, it will be sort of automatic. So a negative feedback system has an overall transfer function. In other words, I could replace this entire block diagram by xs, one big block, ys, and inside of here is gs over 1 plus gh, right? Sg, this is g of s here, right? Notice negative feedback, and the sign is positive. And you could very easily prove that if it was positive feedback, the sign here would be negative. Okay, so you take the block diagram, and what we've done is that this whole thing simplifies to x going into our block. This is the transfer function of the block, g over 1 plus gh, and y coming out. All right, following me so far? Yeah, no, maybe? Make some sense, right? We've mentioned this in different forms a couple of times already. So if we use some of the nomenclature or the labels that are used in electronics, the forward block, they normally say this is an amplifier. So they say that the transfer function of the amplifier is A of S, or capital A. The feedback, now this is a little feedback circuit of some sort, whatever it is. And they normally call the feedback in the electronics text, they use the symbol beta. So A is the forward, and beta is the transfer function of the feedback part, whatever that feedback circuit is. And in the specific case of an oscillator, the feedback now, look what we've done here. We've done instead of negative feedback, we have positive. So from before, we know that it was going to be g over 1 plus gh for negative feedback. I told you if you change the feedback from positive to negative, then this is going to change. Now, for positive feedback, you're going to have a negative sign here. And if we change to the nomenclature that they use in the electronics books, what we're going to get is that the transfer function of this positive feedback system, right, is A over 1 minus A beta, right, times the input. Fair enough? Again, if at any point in time it's not being followed, just stop me and ask. Right. So the part A beta is what the textbooks call the loop gain. So anytime you're reading something or some of the handouts that I have, I'll put up another handout for this. Anytime you get a handout and you see something where the loop gain is so and so, they're referring to A. Notice I've changed it again to the amplifier symbol. So A, the forward block, beta, the feedback. A multiplied by beta is the loop gain. All right. Now look at something. If I somehow were able to make A times beta equal to 1, what I'm going to have here is 1 minus 1. In other words, I'm going to have a 0 on the denominator. If that is the case, AS over 0, anything over 0 is going to make XO equal to an infinite number times Xin. In theory, what that will mean now is if I have A beta equal to 0, the gain of this whole block is so incredibly high that I can almost get an output with no input. The littlest input, however microscopic, down to 0, theoretically, is going to give me an output. Yeah? Everybody's seeing that. It's just a mathematical thing. Of course, it can't happen exactly like that. But if the gain is so huge, then you virtually need no input to get an output. All right? Not you're getting almost at a perpetual motion machine kind of theory here. You know, it can't work in practice, but maybe something is the math is telling us that we can get something like that. So if we can get that where A beta is equal to 1, the system can theoretically be self-sustaining with no input, right? So I'm drawing it over here. So if A beta is 1, we don't need any input, and this system itself can be self-sustaining. That particular product where A beta, the loop gain, as we call it, is equal to 1, is something called the Barkhausen criterion. And this is one of two things that are required. The full Barkhausen criterion. This is one of the things, the conditions that are required for this particular circuit to oscillate. More formally, is that the magnitude of A and beta must be equal to 1. So this here, 1, this, whatever this is, the magnitude of it must be equal to 1. So 1 minus 1 is 0. And then the second thing, in order to get positive feedback, whatever signal goes through here must have 0 phase change. In other words, it must be in phase. It must be in phase with whatever is coming back in. Otherwise, you're going to get, you remember from your physics, if things are out of phase, you're going to get destructive interference and so on. If this is 180 degrees out of phase, then what you're doing is that when you put it into the summing junction, what you have done is to change the positive, adding the positive feedback to a negative feedback. If you go the full 360 or 2 pi, then it goes back positive. So you always have to ensure that when the signal, whatever you're taking back to feedback here, must not have a phase change, or if it does, it must always be a multiple of 2 pi, where n could be from 0, in order to ensure positive feedback. Make sense? Yeah? Following me so far? Let me know if anything is not clear at this point, okay? So if, again, A and beta are frequency dependent, we are dealing with circuits here. So the responses of these circuits, both of them, depend on the frequency, F or omega. So they are frequency dependent. At one particular frequency, however, depending on how you do this, at one particular frequency, you're going to get the Barkhausen criterion being satisfied, where A by beta is 1, and that the phase shift through this is 0 or a multiple of 2 pi. A single frequency that is going to happen. And when that happens now, you get a sinusoidal, you get an output from the oscillator being created, and it's self-sustaining. You don't need any input at that point. So this is what we do, A and beta. So if A beta is 1 and Xi is removed, the system should oscillate indefinitely. Of course, because we're dealing with electronics and there are losses in this in the wiring, in the changes in the power supply, components get warm and so on. A beta doesn't stay at 1 all the time. Frequently, it will get to 1 and then it will drop a little bit and then the system will stop oscillating. So typically, what we do is to well, anyway, I'll come to that. Right, so if A beta is 1 and X is removed, we should get our oscillation. If it's less than 1 and you remove the input, the system dies out. If it's greater than 1 and you remove the input, the output is going to do this. So you're going to get it, is going to do this, and then eventually saturate at the positive and negative rails. In this case, it will die out, it starts, and then the gain will do this, and it will just settle down to something. What you want is that it stays, and it just stays and keep going. All right? In practice, so what I was saying, in practice, this is usually what happens. You start with this, and it, because of circuit changes and so on, it tends to drop a little bit, and the output will tend to die out. So what we typically do is to make A beta a little bit greater than 1. And then we adjust, we put some output circuitry that we'll talk about to prevent it from saturating. So what we try to do is more like this one. We try to make the system oscillate, and as it gets up to a level that we want, we adjust the gain of the circuit to kind of just keep it at that point in time. All right, so once it's there, and if it starts to fall, we vary the gain a little bit back and forth. All right, and that's all done automatically because of we're dealing with op amps and so on, and we'll see how that happens. Okay, so this in this first set of stuff is how we get oscillation. First, there are a couple of things. We have to have positive feedback, and we have to have the loop gain equal to 1. Once we have that, we satisfy something called the Barkhausen criterion. And that now, once we satisfy that, now we're able to get a self-sustaining output for the oscillator. All right? And that also gave us a little brief introduction onto the of block diagrams. Okay? So let's watch now and see how we work that in practice. All right, so share something else now. All right, which should be this one. Okay, so what we're going to do now is to spend a little time looking at the first of the RC circuits that give us this sort of behavior. So we just said that. And always remember that, and you would see it as questions that is asked almost every exam and so on. What are the conditions for oscillation, or what is describing what you understand by the Barkhausen criterion and so on. If you ask that, what you understand by it is that in an oscillator, all right, and you could draw a simple block diagram like that. The loop gain A beta, the magnitude of the loop gain is 1, and that the phase change of the feedback system, in order to have positive feedback, any phase change must be a multiple of 2 pi. It ideally should be 0 or a multiple of 2 pi. All right. So if this is just something, it's mathematics, and we're not going to get into here. But if the system contains reactive elements, all right, reactive elements meaning capacitor or inductor, if it contains that, And the oscillator, we have the oscillator operating linear. Remember, we spoke about linear time invariant systems before. The only type of signal that you can get out of this kind of feedback network is going to be a sinusoid, right? You can't get any other waveform out of this. Any other waveform will produce nonlinear behavior. So once you have reactive elements, caps and inductors, you're guaranteed in a linear circuit that the output signal that you're going to get is going to be a sinusoid. All right. So the general principle that we had is that the frequency of oscillation of the oscillator is that frequency at which the total phase shift around the system is 0 or multiples of 2 pi, and the loop gain is greater than 1, is equal to 1, or very slightly greater. And this, of course, is Barkhausen. Right, so you can remember it in this form, or you could remember it in this form, that the magnitude of A beta, right, must be equal to 1, and the phase change as you go through the loop must be equal to 0 or multiples of 2 pi, right, and equal 1, 2, 3, etc. All right. So let's look at the first example of that type of oscillator, and it's a particular type of oscillation called a Wien bridge, and it's based on a network called a Wien bridge network, which is the part that is encircled in the dotted line there. That is half of it. We know, like the Wheatstone bridge network, you have 4 arms in it. So if you imagine 2 of the arms here, half of that is like half a Wheatstone bridge. So the Wien bridge actually has 2 other arms, but we're only using one part of it here. So this is the Wien bridge oscillator, and notice how it is composed. The shaded part, you have 2 equal resistors and 2 equal capacitors. In one arm here, the resistor and capacitor is in series, and in the other arm here, the resistor and capacitor are in parallel. Let's see what that does to us. If you were to look just at the RC network itself, notice that we have an output here, V out. Let me just write that a little bit better. V out here is grounded, and we have signal coming in here, right? So if I were to redraw the circuit here, in fact, let me put it a little bit, just to match I have V in because this is the input to the network. This is V out here, right? So V in, this is the signal coming back into the Wien bridge. V out is a signal going into the op amp here, right? So the output of the bridge itself to match what we have here. If I were to do some simple circuit theory, V out over V in, each of these is just 2 impedances in series. So the output simple an impedance divider. So V out is Z2 over Z1 plus Z2. Z1 is R in series with the capacitor. So that's R plus 1 over SC, once we're in the S domain. And Z2 is R in parallel with SC, 1 over SC. Yeah? Ask me any questions, of course, if you're not following, right? If you substitute and you carefully simplify, you're going to get an expression looking like the one on top. That V out over V in is SRC over S squared R squared C squared plus 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 plus. All right. For reasons that we'll come to in when we talk about a Fourier transform, it is usually preferred. It is not wrong to have it this way. Eh? So if you ask, if I ask you to derive the output for the Wien bridge and you leave it like that, you'll get the marks. Okay. But it is preferred, and we'll see why. But it's preferred to divide through by the R squared C squared. In other words, keep the coefficient of S squared as 1 and express it in this form. So the transfer function for this network is S over RC over S squared plus 3S over RC plus 1 over R squared C squared. Right? Just now, have a second. This type of transfer function is what is termed a bandpass response. We will get to that. We have a little section of the course that will deal with filters, and you will see what bandpass means. And the standard form of that looks like this equation down below. Let's compare the two. And in fact, you could deduce some of the behavior straight off from it. If I compare those both equations and assume this thing Q is 1, forget what Q is. All right. If you look at it and compare straight off, you can see that omega naught squared is equal to 1 over RC squared. In other words, omega 0 is equal, omega naught is equal to 1 over RC. This is called the center frequency of the bandpass. And if you look at where, if I substitute 1 over RC into this expression here, you will see that V out over V in at omega 0 is 1/3. In other words, at omega 0, the gain of this circuit that we have here, the gain is 1/3. So it's oscillating at 1 over RC. And the gain of the circuit is 1/3. All right. What did we say the gain is supposed to be in the Barkhausen criteria? Remember? A beta is supposed to be equal to, anybody if you remember? A beta is equal to from what we just did. Right, 1. So A beta is equal to 1. So if I'm telling you that this particular network has a gain of 1/3, when I hook it up to the amplifier like I have here, right? If this thing in the dotted line has a gain of 1/3 and the entire amplifier is supposed to have a gain of 1, it means that, or the entire oscillator, sorry, is supposed to have a gain of 1, then this amplifier must have a gain of 3. Right? So whatever you do with R, B, and RA is supposed to give this. This is an inverting amplifier, sorry, a non-inverting amplifier, right? Which is why, and notice that we have the positive feedback here. So it's a non-inverting amplifier. The gain here equal to 3. The gain of the network here is 1/3. So 3 by 1/3 is going to give us the loop gain of 1. All right. And then now, let's see something about the frequency and what is actually doing here. If you remember from the Laplace transform, that variable S has a real part and an imaginary part, j omega. This was a frequency dependent part, you notice, which is why we use that particular designation here. So if I want to get the frequency response here, and we're going to prove this in a couple of weeks when we do the Fourier transform. If I'm given a transfer function and I want to get what the frequency response of the transfer function is, what I do is that I take wherever S is, I substitute S equal to j omega. In other words, I see what the j omega part of that transfer function is looking like. Let's see why. We will get the full explanation in a couple of weeks here, but for the time being, just accept that if I'm given a transfer function and I need to evaluate how the transfer function behaves with frequency, wherever I see S, I substitute j omega, the full j omega, okay? So if I do that to the transfer function that we have above here, I'm going to get an expression looking like this, j omega over RC squared, then minus omega squared, another 3 j omega over RC and 1 over omega RC squared here. Now notice something. What would make, if I give you something like a a complex number, a plus jb or 1 over a plus jb, the phase angle of that, right, is in this case minus b over a. If I want that to be equal to 0, I have a couple of ways I could get that. Well, in this case, if I give you 1 over 1 plus a plus j b, if I want this phase angle to be equal to 0, b has to be equal to 0. Fair enough? Make sense? If b is equal to 0, then I have inverse tan of 0, which is 0. Yeah? Make sense? Come on, let me know. Right. So the other thing I can look at this expression here. So I now have a different one here. So if this was simply one, if I didn't have this j on top here, and I wanted to make the expression have 0 phase change, all I had to do is to make sure that this particular part was 0. Of course, that doesn't make sense at this point in time, because if I make omega equal to 0, then I don't have an oscillator anyway. But look at the funny thing here. If I were to find a way where this bit, the real part here, is equal to 0, then what I have is j omega over RC over 3j omega over RC, which is basically a third. Yeah? The j omega parts cancel. That now, this is a constant. This has 0 degrees phase shift. So I can also do it in this case if I were to make this part, the omega squared plus 1 over r squared c squared equal to 0. And what value of omega will make this equal to, will make this? If minus omega squared plus 1 over r squared c squared equal to 0, you get again that omega is equal to 1 over rc. Yeah. So in other words, this particular circuit also, we're proving here that one, the gain is a third. It oscillates at omega naught equal to 1 over RC. The gain is a third. So if we multiply it by the AV of the op amp, we get 1. And then the phase shift at omega naught is equal to 0. So we're satisfying the Barkhausen criterion now. If you do that, and this is just a plot of it, if you plot what the gain, what the system response and the phase angle looks like, you notice that as the frequency approaches 1 over RC, right? As omega approaches that, or F equal 1 over 2 pi RC, doesn't matter. As you get there, the gain becomes 0, and the phase shift is also 0. Sorry, the gain becomes a third, and the phase shift becomes 0. So you take this now and you multiply this by a gain of 3, and you get an oscillator coming up. So the network produces the signal at frequency omega 0. Both the signals are in phase with the output and is attenuated by a factor of 3. So you pass it through an amplifier and you get your oscillation being occurring. Yeah, it's fairly simple if you think about what you're trying to do. One, you're trying to find a frequency of oscillation. That is where this network comes in. Having found a frequency of oscillation, you then determine what is the gain at the frequency of oscillation. And then whatever that gain is, you have to multiply that by something to make the overall gain 1. And then you also have to show that the phase shift at the particular frequency of oscillation is 0. You need both things to happen. So you need the gain of 1 at the frequency of oscillation, and you need a phase shift to be either 0 or a multiple of 2 pi. And once you could do both things, then the circuit will oscillate at the frequency omega 0. So in this case, how do you design this? It's a simple network. So what you start off doing, of course, you need to decide what is omega 0. So you're starting off with that, right? What frequency do I need this thing to operate at? You choose a reasonable value for the capacitor, and after you have been working with the circuits for a little while, you get an idea of a ballpark value of a capacitor that will work. Then using omega 0 and C, you calculate a value for R. Right? Remember, omega 0 is 1 over RC. So you start off knowing this, you choose this, and you calculate this one. Then you need a gain of 3 on the op amp. So you pick a value for RA, and then you calculate the value for RB. Remember, it's a non-inverting amplifier. So you calculate the value for RB to make the gain 3. And as we will see, what you need to do really to make this thing, it will start off oscillating, but it will die off after a little while. You need to adjust RB a little bit, and we're going to see how that will be done in a class later on. It's done with a little bit of extra electronics, nothing too drastic. Okay? But if you make the gain 3, then, and you power on the circuit, you're going to get a nice clean sine wave at omega 0 being created. Okay? One of the little issues with this is, of course, it's not easy to change the frequency. If I have to change the frequency of this, I have to change either both C's or both R's together, because they have to match. The C's have to match and the R's have to match. So usually for a Weinberg type of oscillator, if you have to do frequency changing, you have to have the capacitors and the resistors change in pairs. All right, and this is the kind of way that you do it. So you have the resistor. This is what they call a ganged or linked potentiometer and a linked the linked capacitor. So basically there are 2 switches, and as you change one, it changes both sets of values together. All right, so like in your lab, when you sit down with the signal generator in the lab and you're changing the range, when you change from let's say the 10 kilohertz range to the 100 kilohertz range, when you switch, what it would have done is to change a pair of capacitors from one frequency to the other. And when you turn the dial in front of the signal generator, the dial with the vernier gauge on it to get the frequency thing, what you're doing is changing these two potentiometers together inside of it. So the push buttons in the signal generator change these capacitors together, and the what do you call it? The dial in front with the vernier scale on it will change these 2 resistors together. Yeah. So questions. All right, what we did, we started off, first off, what was an oscillator, and then the conditions that are required for the oscillation. You must have positive feedback, you must have a loop gain of 1, and you must have, well, the positive feedback is created by either having a gain of 0 or a gain of a multiple of 2 pi. And then we saw the first practical implementation of that, which was this particular circuit called the Weinberg oscillator. And what it does, it uses a parallel and a series combination of a resistor and a capacitor to create the frequency network for us. And then it uses an op amp to give us the gain required to create the loop gain of 1. And if you do that correctly, you work out notice that this particular transfer function has nothing to do with the op amp at all. This is just the network itself. So it's only the RC network is the important part of the oscillator. The op amp now is to give you the gain of 1. All right. And from this morning, if any of you all recall, we did a general purpose second order system this morning in signals, and that particular one had the transfer function was a omega naught squared over s squared plus 2 zeta omega naught s plus omega naught squared. Notice again, there's a little difference here because this transfer function has a 0. The one that we did this morning didn't. But if you look at the denominator, notice the form of the denominator is similar to what we did before. And the omega naught squared is still the 1 over RC squared. So even from what we did this morning in signals, you could see that omega naught is 1 over RC. Yeah? And if you substitute it, you could get this some of the behavior here. What we did this morning was did not have any zeros on it. It only was a transfer function that only had poles. This one is a little bit different, but you can see the connection to some of the stuff that we also did. If you did the signals class, if you're doing signals and you were in class this morning. Yeah. All right. So if there are no other questions, I will stop. Everybody all right with that? Look at, review the material and so on. And when we meet in class, we will, tomorrow, we'll go it over again, answer any questions, and then we're going forward to look at some other oscillator networks that we have to discuss, okay? Some other RC networks, a little bit different, but the same sort of thing. We have to analyze it to see what is the loop gain, first off. Well, first off, we get the transfer function. Having obtained the transfer function, from the standard form of the transfer function, get omega 0. From omega 0, get what the gain is, and then put it through an amplifier to make the loop gain 1. And then you make sure, verify that the phase shift is 0, and we're good to go. All right? Okay, so that is it for today. I will stop the recording, and I will see you all in class tomorrow, bright and early. And just stop the recording.